so
Yeah.
we can start. I'm sharing the slides, but just let me know. I mean, I guess.
Yeah, I can see it. Perfect.
Okay, just let me know next slide. And
Yeah.
I mean, it's just a recap of yesterday's, introduction. So it's nothing.
Sounds lovely.
Hello, Randy.
Hey, Randy. All right, we are on the top of the hour, so we can start. Hello, everyone. Welcome to session 3 of ANRW 2021. So this is day 2. Andra and myself are pleased to welcome you to this third session in which we will talk about interconnection and routing. So we have 2 talks. One from Romain Fonturg from IIJ, talking about hunting BGP zombies in the wild. And the next talk is going to be on meta-peering towards automated ISP peer selection by Shahzeb Mustafa. My name is Amrish Fukia. I work for the Internet Society as an Internet measurement and data expert. And I guess we can start. First of all, let me introduce Romain. Romain is a senior researcher at IIJ. His current research interests include traffic modeling, network, data analytics, and anomaly detection. Miteko, can you please play the video for the first presentation, please?
Hello everyone, this is Romain Fontaine from IETF Research Lab, and today I will present our latest results on BGP zombies. So first, let me explain what a BGP zombie is. So this figure represents how one prefix is seen by RIS routers. On the y-axis here, you have all the RIS routers, and on the x-axis, you have time. The prefix we are looking at is one of the RIS BGP beacon prefix. And the green circles here shows that the prefix is announced by one of the router. Then the green line shows that the prefix is active.
Yeah, sorry, just 1 second. I misconfigured the audio device, so the volume was very faint. Just give me a couple of seconds and I'll fix this.
Sure.
So while we wait, maybe I can just tell everybody that we corrected from yesterday, and now you do have slides in the data tracker in case you want to go there and check. At least all the talks from yesterday and today have the slides there. So I just wanted to add that. Thanks.
Hello everyone, this is Romain Fontaine from IETF Research Lab, and today I will present our latest results on BGP zombies. So first, let me explain what a BGP zombie is. So this figure represents how one prefix is seen by RIS routers. On the y-axis here, you have all the RIS routers, and on the x-axis, you have time. The prefix we are looking at is one of the RIS BGP beacon prefix. And the green circles here shows that the prefix is announced by one of the router. Then the green line shows that the prefix is active in the router routing table. And the red cross shows that the prefix is withdrawn by the router. So here it means the prefix is active for 2 hours, then it's withdrawn for 2 hours, and then it's announced again for 2 hours, and withdrawn again, and announced again. And this is what we expect from BGP beacons. But you can see that there is 3 lines here that represent 3 routers that think that this prefix is active during this time, even though we know that the prefix was withdrawn by RIPE. And this is what we call BGP zombies. So here we have 3 zombies. In summary, a BGP zombie is an active entry in a routing table that correspond to a prefix that is in fact withdrawn by its originators. So in the past, we've looked at these BGP zombies, and we used BGP beacons to do that. That was what we published in PAM 2019. But it didn't really tell us anything about the regular prefixes we're using on the internet. And this is the goal we set for this work here. We want to monitor BGP zombies for regular prefixes and see if it's as bad as what we've seen for beacons. So for beacons, the finding zombie was very easy because we knew already when the prefix is withdrawn and when it's announced again. But here, because we are looking at any prefix on the internet, we have to find out when an originator is going to withdraw a prefix. And to do that, we are looking at a metric, which is the number of active routers for a prefix. It's shown here in that figure. So that metric range between 0 and 1. 1 means that all the routers we are using see that prefix as active. So it might decrease a bit, and there's some noise in this metric, just meaning that some router might withdraw the prefix. There is some topological change that can happen on the internet that could cause this noise. But when we see a significant drop, and it's when things start to get interesting, either the drop will go down to 0. In this case, it means that all the router we're using, they all withdraw the prefix. If it goes down and then up again, and then stabilize, that means this there was some significant change in the topology. So maybe that prefix was withdrawn and then reannounced by the same origin or different origin. But what is interesting for us is to see when there's a significant change, a significant drop, and then this metric, the number of active routers, is stable but at a low value. Here it means that only a few routers didn't withdraw that prefix, and if it lasts for a certain time, then we're gonna say that this is a BGP zombie. So this is our definition of the BGP zombie. When we see the majority of the router have withdrawn the prefix, we're gonna wait 90 minutes, and after 90 minutes, if we see that the prefix was not completely withdrawn, or it wasn't reannounced, then we're gonna say this is a zombie. You can check the paper for some of the details why we use 90 minutes. We have some explanation for that in the paper. I don't have time to explain it. So using this very simple zombie detector, we analyzed 6 years of BGP data and found 6.5 million of BGP zombies. And we looked at different things in these zombies. First, we ran some sanity checks. I will explain the next slide. And we also look at some of the characteristics of zombies in the wild. One of the first sanity checks we've done is to look at what we call the state covariance between respires. So here's an example of a zombie that appears in AS3. So AS3 is reporting a path to a certain prefix. This path is AS3, AS2, AS1, AS0. So AS3 tells us that it can reach that prefix through these ASs. But we have access to one of these AS through RIS, and that AS tells us that it has withdrawn this prefix. So because those two information are conflicting, we say that the states here are incorrect. One of the respires tells us that it has a path to a prefix, but on this path, we see that one of the AS has actually withdrawn the prefix. So this really tells us that there is in fact a zombie, and it's not a misclassification. So we use that to validate our result. But to do that, we have to have zombie paths with at least 2 risk pairs in the US path. So about 68% of the zombie paths we detected have 2 risk pairs. And for this 68% of paths, we found that almost 95% of them have incoherent states. So that means they are really zombies. And the rest are not really conclusive because it could be that the 2 risk pairs we have access to, they both are affected by the zombie. So we cannot really say if it's a misclassification or not. Another thing we looked at is where are the beacons in our result. And we found that the risk BGP beacons account for 3.2% of all the zombies we detected. And 3.2% seems to be a small value, but actually it's very big because there is only 27 risk beacon prefixes out of the over 800,000 prefixes we have on the internet. So only those few prefixes have created a lot of zombies. And one of the questions we had then was, okay, maybe noisier prefixes like BGP beacons are more prone to zombies. And this is what we looked at in this figure. We took the prefixes that had a lot of zombies, and we look at the number of updates for these prefixes. And you can see that as the number of updates is increasing, the chance to have zombies is also increasing. One takeaway from this is that beacons are not really representative of what we observe for the regular prefixes. And this was especially true for IPv4. And we also looked at zombies for popular content networks. So we took 42 ASN that are commonly found in the top 15 Alexa, Umbrella, and Majestic list. And we looked at how many zombies they had. Here's the ranking of this ASN and over time. And you can see that some of them had zombie almost every month. We did this only for 2 years in 2018 and 2019. And we looked a bit more at this ASN. We looked at a different characteristic. And what we found was that the top ASN popular content networks usually have also either like they announce a lot of prefixes or they are very long AS path lengths. And if we think about it, it kind of makes sense if we assume that BGP zombies are due to bugs in routers, then a long AS path length means that it's going to imply more routers and thus more chance to hit one of these bugs. And finally, in the paper, we looked at some of the side effects of BGP zombies. We found that 77,000 zombies created the tools. For example, it would be cases where the path will follow backup links instead of the usual AS path we'll see. And we also found that some zombies have an origin that is different than its covering prefix. Because that route is stuck, then we might have a wrong origin AS information. I won't give the detail here, but you can look at the paper. In some cases, the BGP zombies can create routing loops, and we found over 400 of potential routing loops in our result. I also advise you to look at this presentation from PLNOC last year, where they give a concrete example of routing loops, and they also did traceroute to show that. Okay, so that concludes my presentation. In this work, we look at BGP zombies for regular prefixes. We found that zombies are widely spread. We found zombies for very popular content networks. It's even though it's widely spread, it's not as bad as what the our past study using BGP beacon was suggesting. And also here in this work, we find some interesting side effects from BGP zombies. Thank you for listening.
All right, so you can start queuing up and ask question to Roma. Is Roma, are you here? Yes, great. Good morning.
Everyone. Thank you. Good morning.
So do we have questions for Roma? If not, I have a question for you. My first question would be, what do you think could be the cause of these BGP zombies? Is it faulty routers? What could be the causes? Yeah.
Thank you. That's a very good question, and that's definitely something is missing in our study. It's simply missing because it's very hard to check all the causes of zombies. The main cause we think is yes, faulty routers and bugs in routers. But yeah, because it's just like very hard to check all the different software version, and in it's probably a lot of corner cases where things don't work. It's hard to check, yeah, but that's what we think is a problem.
Okay. And do you have an idea of what perhaps could operators do or implement to mitigate the effects of zombies?
So what we've heard from operators is they sometimes see those zombies appearing, and the common practice is to re-announce prefixes and re-withdraw them, because so when you withdraw a prefix, you have like a very small chance that a zombie appear. And by just re-announcing and withdrawing seems to usually remove zombies that appears. We've heard from some that they just reset their whole BGP session, which is a bit brutal, but that's
the good old way.
Yeah.
Yeah.
But yeah, I think the main problem for operators is to monitor this, to know that there is in fact problems.
Right.
And for that, for the paper, we do monitor zombies, but in real time, it's sometimes a bit hard to do, because you have to, if you use RIS and route views, that's a lot of data to process. So it can be a pain of like taking all this data. But still, like RIPE provides some tools like BGP Play, for example, where people can look at how their prefixes are seen by RIS.
Okay, I see we have one person in the queue. Colin, you can proceed.
Hi, can you hear me?
Yes.
Yes, good. Hi, nice talk. So this is not even close to my area, so this question may be may make very little sense. I was wondering if you were seeing any difference in behavior between IPv4 and IPv6 prefixes, given that the interpretation is that it may be router bugs and they may be exercising different code paths.
Yeah, very good question. So in this paper, I don't think we've done much comparison between IPv4 and IPv6, but we had a previous paper on that, and we've seen, the bad news is we've seen much more zombies in IPv6. And one reason we really dig into the results for that one, and we saw that one of the network was creating a lot of zombies, and we contacted them, and they were saying that yeah, they had some problem with their IPv6, and they were restarting their BGP sessions when they had customer complaints.
Yeah. Okay, great. Thank you.
Thanks.
Join the queue. Please proceed.
Hi, can you hear me now? Yeah. Hi, Ramon. Thank you so much for the talk. Very interesting. So I'm just wondering, because I mean, you process so much data, and I know that going through all the information from RIS and from ROGVIZ is just, you know, complete a work in itself. So thank you so much for taking the time to do that. So maybe I missed this. I'm just wondering how much of what you're seeing as zombies are actual zombies, and how much is just, you know, some hiccups or accidents that may occur, or have you been able to separate reliably these two? And maybe a follow-up is just, have you seen like some big offenders in the sense of, you know, somebody who may, you know, generate too many zombies, or do you see sort of like a very skewed distribution in the you know, origin of these zombies? So again, thank you so much.
Yeah, thank you. That's a very good question too. So in this paper, we didn't really look at the source of zombie, but the previous one did a bit more work on that. And we found, so we had a technique to find what is the source, which is where the zombie created. And it was not really like there was like not one big offender. It was like changing quite a lot, and that also gave us some more evidence that there is like those bugs. It's a bit random, like how the zombie are created. So last time we worked with BGP RIS beacon, and they are just doing the same thing like over and over, like every 4 hours. But even though they are always doing the same thing, we could see that zombies appear at different places in the network. So even though we have like this very controlled environment, you know, things were changing all the time. And for the first question is how we check like they are really zombies. So in this paper, we did like some of this sanity check, like the difficulty with this work now was that we're working with past data. We use like 6 years of BGP data. So it's very hard to go back in the past and check, you know, what really will happen. But the previous studies, we did run trace routes. So every time we found a zombie, we run trace route, and we could confirm that every time, like we see like a few routers that will forward the packets, and then we receive ICMP message saying that the network is unreachable. So we could confirm that, and I don't remember exactly the number, but it's like over 90% were really zombies.
Thank you so much. Thanks.
Thank you.
All right, so I see Jared in the queue, so we will take the last question before closing. Go ahead, Jared.
Yeah, Jared Mach, Akamai. I mentioned that because in your paper you highlight a number of our prefixes that apparently regularly get stuck and such. Yeah, I think there's a lot of things that contribute to that on our side, and we've definitely been trying to improve some of our prefix stability efforts as well. Because we have a large set of distributed deployments. And then a lot of these, like the 16625 AS originated prefixes, those are all coming from BGP speakers that run on either on routers or on servers. specifically that may be more likely to actually have some negative operational impacts when those things are put into service or taken out. And when we've been trying to improve the prefixes, so I'd be interested to know or see if you're still seeing this from us and if it's improved recently, because we've been undertaking a number of efforts to improve this.
Oh, that's okay. That's very interesting. Then I guess, yeah, we could check again and see like if there was some improvements. But again, one thing I'd like to mention is I remember for Akamai we see because you announce a lot of like very small prefixes, I think at different places in the network. Sometimes we see a very long AS path for these prefixes, and I'm guessing that so zombies will appear for those like very long AS paths, and I'm guessing that this has like little to no impact for your traffic, because that's probably where it's not the place where you're gonna direct your clients. But
yeah, we have a lot of distributed unique deployments, as well as we now have actually 3 different backbones that we operate that interconnect all of our sites together. So depending upon where the regional interconnection is for the distribution of the content into a customer network, you know, in Japan it might be different than in India than somewhere else. You know, obviously you'll see different AS paths, you know, for those based upon the relationships we have with the service provider. So it's quite possible that, you know, some of the prefixes might be negatively impacted depending upon that upstream provider, you know, network property. And we actually we have teams who are actually working full time, you know, going and chasing things like that around, as well as systems that kind of monitor and detect it. But they tend to just take things out of service, and then a human has to go and chase down and figure out what happened. You know, we quite often see, you know, I think it should be no surprise to anybody who's looked at BGP research. We see a lot of interesting events all the time, and so when the systems just take stuff out of service, automatically it's really, you know, it's doing that to improve the customer experience, and that happens all day, every day.
Yeah, that's very interesting. Thanks.
Thank you, Jared. So this brings us to the end of your presentation, Roma. Thank you so much for coming here so early for you. Yeah, thank you very much. So we can move.
Thank you very much.
Bye-bye. We can move to our next speaker, who is Shazeb, who is a PhD student at the University of Central Florida and is currently working as a research assistant at the Networks and Wireless Systems Lab. His key interest areas of research are network architecture, internet peering, and data analytics. Please play the next video, please.
Hi everyone, my name is Shazeb Mustafa and I will be presenting meta peering today. So finding a suitable ISP to pair with is a slow process, and ISP admins put a lot of effort and a lot of time into selecting suitable pairs. Why is that? Because ISP admins often attend events sponsored by PeeringDB, Nanode, etc., where they network with each other. And using these events, they identify ISPs for potential peering. And after they negotiate, they negotiate traffic exchange terms and conditions, which may include traffic, the max traffic volume they are willing to exchange, or the specific points that they are willing to pair at, or whether or not it will be a public pairing, etc., etc. And then after this step, if and only if both of the ISPs Hi everyone, my name is Shazeb Mustafa and I will be presenting meta peering today. So finding a suitable ISP to pair with is a slow process, and ISP admins put a lot of effort and a lot of time into selecting suitable pairs. Why is that? Because ISP admins often attend events sponsored by peering DB, Nanode, etc., where they network with each other. And using these events, they identify ISPs for potential peering. And after that, they negotiate traffic exchange terms and conditions, which may include the max traffic volume they are willing to exchange, or the specific points that they are willing to pair at, or whether or not it will be a public pairing, etc., etc. And then after this step, if and only if both of the ISPs agree to the terms and conditions, the BGP forwarding rules are written, so the deployment actually takes place. So, I mean, overall, since the whole process requires a ton of manual work, it is extremely slow, and it oftentimes takes a couple weeks to months. And even with such an elaborate and lengthy process, finding the right peer is hard. And say you've put in like 2 months into selecting your peer, it's not guaranteed that it's going to be an optimal option. Because see, the internet is far more dynamic than these interconnection deals, which means that during the negotiation and finding process, there plenty of great peering opportunities are discarded. Under or overestimation of various metrics can lead to future disagreements. ISPs can be part of suboptimal relations knowingly or unknowingly. And we have also seen cases of ISPs ending peering contracts because of disagreements and violations. Now, bad selection can also mean that your resources are not optimally utilized. So, sort of your load balancing factor is suboptimal. And in the bigger picture and in the longer run, such relations, suboptimal relations, or disagreements, or missed opportunities, everything, in the longer run, such relations can hurt ISPs, both ISPs, financially. So it's clear why it's so important for these to be optimal, and along with that, to be dynamic. So if you've identified an issue, you can fix it quickly. Now we present meta-peering, a tool that will help identify optimal peering ISP pairs, and it also gives you the best peering contracts. So say for two given ISPs, we need to decide whether or not they should be peering. And if yes, which particular locations they should be peering at. So we first calculate the traffic matrices for both the ISPs, which is sort of their internal traffic flow. We calculate these using POP, or points of presence locations, which are locations where an ISP has connection capability. So this can be an IXP or a private facility too. We also identify the locations where both these ISPs have a presence, because these are the points where peering is possible. Then we gather the gridded population data for the United States, which basically divides the whole country into small segments. And now we know the population for each of these segments. And we take all of this data, all of these computations, and feed them into this policy generator machine, which churns it up, extracts all the useful information. It knows what's important, what's not. So it does that while respecting any additional peering policies injected using the policy filter. Now, how does it do that? It basically gives out three different outputs. The first is, so it basically uses the POP locations and the population data to construct an overlap map between the two ISPs. And what it represents is the number of people each ISP presumably covers, and how many more people can become accessible with a peering deal. This is summed up in the affinity score. The next one is it uses the same POP locations and also the traffic matrices to give out peering willingness scores for each of the common POP locations from the perspective of both ISPs. So the overall willingness score for a particular peering deal is just the average of these scores at particular points. Third, it optimizes the selection of POP locations using the individual willingness scores to generate acceptable peering contracts. We then take the geometric mean of the willingness score, which is the representative of the willingness to pair, and affinity score, which is the representative of the non-overlapping areas and population, to get the felicity score, which tells us whether or not these ISPs should pair. Now, please note that these scores are novel. They're not like an industry standard. We came up with these scores, and we have discussed how we came up with this and what they represent. So with the felicity scores, ISP admins can set a threshold. Okay, if this pair has a felicity score of more than 0.6 or 0.7, we'll be pairing. Otherwise, we will not. So this is the deciding factor for whether or not they should be pairing. And along with that, we give them the acceptable pairing contracts that, okay, if you decide to pair, these are the locations that you should be pairing at. Now, both of these results can be used by ISP admins to decide whether a pairing deal will be worth it. Now, in an effort to expedite the development of this model, we have deployed a web application to showcase the workings of this tool. These screenshots provide an overview of the website. For Sprint and eBay, we can see the overlap map, which is calculated using the POP locations as mentioned earlier. We can also see the willingness scores for each of the contracts that are possible. Not all of them are listed in the screenshot, but they are possible. And at the bottom, we can see a sample contract recommendation, which is given Sprint and eBay decide that they are pairing. Meta pairing, our tool, recommends that they should be pairing in Los Angeles and Chicago. So the website lists top 3 such contracts. So this is the best one, and then there's the second best option and the third best option. And just for reference, here's another example for Columbus and eBay. And in this case, the same overlap map is given, the willingness graph is given, and a sample contract is given. But in this particular case, our model does not recommend pairing. But in case they do end up deciding that they should pair at San Jose and Ashburn. We tested this model on 23 different ISPs, which basically means 506 pairs, using two heuristics. Now the x-axis, we can see on the x-axis we can see the ISP pair type, where A is access, C is content, and T is transit. So AT, for example, means that it is an access transit ISP pair. So the first heuristic, the ISP view, we recommend pairing if any one of the 2 ISPs has a felicity score greater than a certain threshold. In this case, we used 0.55. For the second heuristic, the holistic view, we recommend pairing if and only if both of the ISPs have a felicity score greater than 0.55. The figures show a slightly more detailed confusion matrix, sort of. So the top left is the true positive, the pairs we suggested and were pairing according to data. Bottom right shows the true negative, the pairs we didn't suggest pairing and were also not pairing according to data, CADA. The top right shows the new recommendations that we generate, and the bottom left shows the pairing ISPs that we recommend that they should not be pairing. And it can be seen that there's a lot of missed opportunities and some suboptimal relations as well. We believe that meta pairing is a step in the direction of a more dynamic and automated inter-ISP relation management. And we are working on an extended model, a more complex model, a more complex meta pairing model, which uses machine learning techniques to learn from previous data to learn what's important in a pairing deal before giving out its recommendations. So this concludes my presentation. I hope you liked it. If you have any related questions, I would be happy to address them now.
Thank you, Shazeb, and welcome. I see we already have one person in the queue. Randy, you can go ahead.
Okay. Clear my mind when you're weighting a pair and you is when you say one of the serious weights is population, do you mean the number of human beings?
I'm sorry, can you
I'm
repeat the
sorry, can you
question?
repeat the question?
So,
When you're giving the weight to a particular ISP and you use the term population, are you talking about the number of human beings?
correct, yes, the regional population.
That kind of seems to assume this is all eyeballs. And there's a lot more to the internet than eyeballs. There's content and eye candy and infrastructure, etc. So how are those accounted for?
Yeah, so the metrics that we use assume that traffic is directly related to these eyeballs that as you mentioned, and it's directly proportional to the population around that area. So assuming that there are eyeballs, the traffic originating from that area is directly proportional to the area that all of the pops it will cover. So it's just a heuristic measure which we use in approximating the peering suggestions.
But if you're heavily weighted towards eyeballs, traffic tends to go to eyeballs, not from eyeballs.
For this particular case, we're assuming an even distribution. So 2 eyeballs and from eyeballs.
Thank you.
Thank you, Randy. Do we have any additional question? If not, I might have one. So, Shazeb, for example, did you take into account the cost of peering and also the cost of transit? For example, what percentage of of saving someone would do by peering in your model for selection of a peer?
For this particular project, we have not focused on the economic side, but another project that we are currently working on focuses just on the economic side. So optimizing peer selection based on how much you can save. So that is something that we are working on. Maybe in the future, these two projects combine. But right now in this project, we haven't considered that.
Okay, thank you. Do we have additional questions? I don't think so. If not, I might have another one. So I see that you focus your model based on data coming from the US. So do you intend to expand it to other regions of the world where perhaps interconnection is a little bit different than the US scene?
Yeah, definitely. We've seen that the peering trends and interconnection trends are different, especially for European IXPs. So the reason that we have focused on US is because the model needs to train using peering trends, right? So if we combine two, it'll be a problem. But yes, the same model can be trained for European ISPs where different matrices have different weightage.
Okay.
Simply because how IXPs are established over there.
All right. So I'm watching my clock. So we still have 1 minute. If anyone has a last question or even a question to the previous speaker, please proceed. I don't see anyone in the queue, so I'll hand over to Andra. Thank you very much, Shazad and Roma.
Thank you.
So hi everyone. Yeah, thanks so much. We just are closing session number 3, so I'll invite Edmundo to help us chair session 4. Edmundo, if you could share also maybe the slides, or if not, just let me know and I can share them, just to remind people how we're gonna run the session.
Okay.
Okay. Edmundo, I think we lost you.
I'm here.
Okay, because we don't see the slides. I don't know if should I try to share?
You want to share? Okay. I thought you want to.
Just let me try.
Just a second.
So maybe we can already start now the session, because I think you see my slides now.
Yep.
Okay, great. So I'll just hand it over to you. So thank you so much for helping us with the session. I'll leave you in good hands.
Oh. Okay. Can you see my session slides, or I guess you? I'd like to show these to share my screen. Okay. I was going to share my slides here, but if you have, perhaps it's easier that if you share yours. Okay, so hello everyone. My name is Edmundo de Souza Silva. It's a pleasure to be here, and we have a very nice session on monitoring the internet traffic. Today we have 4 papers, and first paper towards cross-layer telemetry will be presented by Justin Human. The second paper, it's about the spin bit, also measurements, then the detection consumer IoT device, how you detect the IoTs in the wild for the lens of ISP. And the last paper, it's on the evolution of internet flows. So it's the way you are going to run the session. We allow a very short question after each presentation, and then you have a panel at the end, a 15-minute panel. Is that correct, Andra? So without further ado, not to take time from the speakers, let's go to the first presentation. Justin Human from University of Liège. He's on research unit in networking. So please, can you show the video, please?
Sorry, Andra, here. There's no sound for me. I'm not sure if other people have the same issue. I don't know, Miteko, if you can help us with that. Thank you.
Either.
Hi everyone, my name is Justin from the University of Liège in Belgium. And today in this talk, I'm going to introduce you to something that we have called cross-layer telemetry. So basically, we try to find a name as explicit as possible, and I will go much into detail about this. But first, let me remind you some basics. So we moved from a kind of monolithic architecture to microservices. So you can see microservices everywhere now. And there are a lot of reasons for that. Mainly that it's easier and faster to deploy, to maintain, but there are also other reasons. So if you look at this kind of architecture, and let's assume there is a problem somewhere, and I ask you to debug and to find the problem here, you would tell me, okay, easy game, right? But what about this one? So it gets a little bit more complicated, right? So hopefully, for that kind of spaghetti microservice architecture, you have application management performance, which is actually application performance management, sorry. And in this case, more specifically, you have distributed tracing tools. In this talk, I will take Jagger as an example, but you have to know that there are a lot of other alternatives. Jagger is just a famous one in all of them. So such tool is very useful when we are dealing with microservices, and they all have something in common. They all have the same notion, the same concept of trace and spans. So you can see a trace has a hierarchy of trace and spans. So a trace can contain subtraces and also spans. And you can see a span as a unit of work, of code. So this is just a part of your code that you want to monitor, right? And here at the bottom of the slide, you can see a screenshot of the Jagger visualization. So you have basically a main trace, which contains two subtraces, and each trace has some child span. So here a span, and then a span, a child span, etc., etc. So you can see on the left that you have a clear visualization of the flow of the code path. And on the right, you have the time taken by each part. So it's very useful for those two reasons. You can see, as I said, the path taken by your code. So if you execute this one, what is going to be triggered, etc., etc. And you can see the time that it took. But such tool is limited to layer 5 and above. So if you have a problem, low level issue, so a network issue, for instance, well, that's when you're facing problem. And to cite an example, let's assume that my database lookup is slow. So I can see in Jagger that my database lookup is slow because I traced it. In that case, maybe should I just blame the app, or should I put the blame on the server or even the database? Or maybe this is a network issue, or actually it can be anything else. So it's hard to know exactly what it is. So you don't know why, and you don't even know where exactly the problem is. So the only thing that you know is what Jagger tells you. It's that it's slow. That's all. So let's just see a basic simple topology here. So you have the app, the database, and this guy in the middle of the path with a congestion of one of its interface. And so Jagger will just report a slow execution time, right? So when you see this, you will investigate on the app, you will investigate on the database, and actually you wouldn't find anything. So you would be left wondering, scratching your head and wondering why it takes so long. And that's a big problem, because root cause analysis, it's hard in this case. So the goal here would be to also include layer 3 and layer 4 in such tool. And actually, this is exactly what we provide with cross-layer telemetry. And to reach such a goal, we first have to answer two key questions. The first one is, how do we find a way to correlate the traces from the APM with the corresponding network traffic? So back to my example, if you want to trace exactly your database lookup in your code, you want to match the trace generated by the APM with the network traffic, which is the DB lookup, okay, on the link. And for that, we will use IOM. So IOM is just, it's in situ operation, administration, and maintenance. It's actually used to carry some useful data in packets. We have developed it in the kernel, and it should be available soon. Why do we use IOM? Well, we want to kill two birds with one stone. So as I said, it can carry a lot of useful low-level information. So for instance, you have the queue size, the buffer location, IDs of nodes and interfaces from where the packet is coming from and where it's going to, and so on and so on. And on the other side, we just enhance the IOM header to carry so both the trace ID and the span ID. So remember what I told you about the common point of those tools. They all have the same notion of trace and span. So a trace ID and a span ID both represent a unique ID of a span. So that's why we just carry the two. So the first important question is answered. Let's face the second one. When and how should we inject these IDs? So when? Well, we have two possibilities. Either at socket creation or when sending data. So if you think a little bit about it, at socket creation, it wouldn't be enough. Why? Well, because an operator could use the same socket for all connection all along, or you could have, for the same connection, multiple trace. See, if you want to monitor different part of your code, you could have multiple trace on the same socket. So that's not an option to inject those IDs at socket creation. And moreover, you don't want to modify the C library, because you would have to modify also high-level languages, and that's not an option. We want to provide a tool, an improvement to those tools, which is not a burden. So you want to integrate it easily without changing everything. Okay, so we will just select the option of injecting those IDs when we send the data. But now how? So again, we have several possibilities. The first one that comes in mind is to modify the send functions offered by the C library. But again, you don't want, as I said, you don't want to modify everything, because if you modify this, you would have to modify also high-level languages. So not an option. So we are left with two other possibilities, which is to add a new syscall or use a netlink call. Again, if you add a new syscall, syscalls are not always portable. And the preferred way of doing this is usually to use a netlink call. So from a kernel perspective, it's always the best option. So we just select the netlink call as an option. So let me explain you a bit this architecture of cross-layer telemetry. So first of all, we have a client, which is a Jagger client in this case, which is used to add tracing code to your application. And actually, when a trace is available, it will be sent to the agent, which will forward to the collector, which will apply some action on it and then store it in the database. Okay. Now we had a CLT library, which is also a client library. We had the netlink call, and we add an IOM agent and an IOM collector. Okay. So the CLT library is just an abstraction of the netlink call. So the application will just pass those IDs to the CLT library. So those IDs will be injected through a netlink call, and they will be injected where? Well, to the socket. So again, someone will tell, hey, this is a per socket solution. So what if you have some congestion in your queue? Maybe that one packet will be marked with those IDs and it shouldn't be. Well, you're correct. And we are currently working on a perfect solution, which will be per packet. So it comes with a lot of other challenges, but I think we are pretty close to a perfect solution. But right now, this one is working pretty well, except in the corner cases I mentioned. But again, the main goal of this one is to have some useful info to debug. So from layer 3, layer 4, as long as it's low level. It's not that important that you have a perfect match between the connection and traces. If you want a perfect match, then stay tuned and we will post the next version, which will be a lot more precise. So back to our architecture. When there is a request, so here HTTPS request, or it can be whatever it is, as long as it's network traffic. So when the packet goes out of the interface, it will be marked with the IDs that were injected here, okay? And so actually the application, or it's not important if it's an application, as long as it's a node at the other side, and you have an IOM agent that will run on this part, and this one is responsible for gathering IOM data, and it will forward those to the IOM collector. And this guy will just correlate IOM data and any data that you want from layer 3 and layer 4 with the IDs that you have passed. And so it will send this to the Jagger collector. So this is a correlation request. And so the Jagger collector will be responsible for just storing the correlation inside the database. And actually, as a result, you can see directly in the Jagger visualization IOM data or layer 3 or 4 data as you want, as I said. So back to our example, you have the application database. We introduce we simulated a congestion here on this guy on its interface. And as you can see, so this is the first node. So this is the app, second node and third node. So the second node is this one. And you can see that the egress queue is increasing. So if you are the operator, now that you see this, well, you directly find root cause analysis, okay? So you can see, okay, there is a problem in the queue. Maybe I could rebalance it, or you are now capable of applying some actions to solve the problem. But again, without cross-layer telemetry, you wouldn't have those data. So the only thing you will know is that it's slow, once again, okay? So let me conclude on this talk. I definitely think that it's a hot topic in the industry. So I've heard that there is a lot of interest on this one. And I do believe that CLT solves a lot of challenges in the tracing world. We are still working on some part to improve it. So I mentioned earlier another version which will be per packet. So to have a perfect correlation and match solution. And there are also some other things to improve, but not that important. So I insist on the fact that this solution is working. So this is something that you could use right now if you want. And there is a link to the GitHub repo, so feel free to have a look at it. There is also a video to demonstrate how it works. Everything is explained there, so feel free to visit it. And that's it for me. Thank you very much for your attention. Feel free to contact me on my email address, or you can ask me a question right after this. Thanks again. I can't hear you, Edmundo.
Have to press allow to allow. So thank you very much for your presentation. Very nice too. Let's see if there is anyone in the queue right now to ask questions. I guess people are shy at the beginning, but I have one question. Do you foresee, because in your implementation, if I recall, you have to do some stuff by hand once you get all of the information. So do you foresee instead of manual intervention, can possibly implement potential to automated analysis that could be attached to your tool? Or have you thought about that?
Yeah, well, we could, but you have to know that below CLT, this is IOM, and so this is the configuration of IOM. That is the biggest part, actually. So operators using IOM usually configure it by hand, but again, we could provide some tools to automate it. So we could also provide a way to merge everything to the APM tool, but maybe it will be a lot of burden for each tool. So I think it should be better to keep it kind of decentralized and maybe provide some tool to configure IOM. Yeah.
Okay. Thanks a lot. Let's see if there anyone else in the queue. It's a nice thing of being the chair. I keep asking questions then. In your paper, you have set up experimentation in the lab. Are you planning anything in let's say, real setup, or I'm wrong, you already did that?
No, of course, you're right. So it was a pretty limited test bed, just for the sake of the paper, but we are definitely planning on expanding the test bed to have some more real test cases.
Mm-hmm. Thank you. And as you said, is everything is free, right? I can just
yeah, it's free available.
And try to. Okay. Okay, so if I'm not mistaken, okay, this is just, we are going to have a panel afterwards. So I think we should proceed, and I please ask you to remain until the panel. So thank you very much for your presentation, and see you soon. So let's go for the next talk. Okay, I guess it's going to be presented by Ike Kunzen from RWTH Aachen University. He's a PhD student and a researcher. So please.
Hi, my name is Ike Kunzen. In our work, we have investigated the four spin-bit cousins L, Q, R, and T. And in this talk, I would like to share with you some insights on their performance regarding packet loss measurements. Before I go into more detail on the different spin-bit cousins, let me first give you a quick intro why work on them is actually meaningful. I think it is safe to say that network measurements have always been important to get a better understanding of what is going on inside of the network. However, measurement techniques have typically been developed independently from protocols, and thus they oftentimes depend on externally visible protocol semantics. A prominent example are TCP sequence numbers and acknowledgements, which can be used to compute the round-trip time of a connection. Let me quickly illustrate that with a short example. What we have here are two hosts interconnected by a network probe in the middle. If the host on the left-hand side now sends a packet with a certain sequence number, the network probe in the middle can store that sequence number and then basically start a timer. The packet is then forwarded as usual, and the host on the right-hand side then answers with a corresponding acknowledgement. As soon as the acknowledgement then arrives at the network probe can basically stop the timer and compute the right-hand side half of the round-trip time. Unfortunately, such techniques are no longer possible in times of encrypted transport protocols such as QUIC, because there the protocol semantics are no longer visible to an observer. To still allow for meaningful measurements, the QUIC standard features a special purpose bit, and that is the spin bit. It is a dedicated bit in the QUIC short header and visible to on-path observers. While the spin bit allows for round-trip time measurements, there are also other important network properties that one might want to measure. In this context, there's an ongoing discussion in the IPPM working group focusing around 4 different proposals that are similar to the spin bit but enable packet loss measurements. Let me quickly explain how they work in the simple example. So we again have a server on the left-hand side, a client on the right-hand side, and now a network probe in the middle. But this network probe now is only able to capture the traffic on the downstream path, so from the server to the client. The first spin bit cousin is the so-called L bit, and it builds upon end-host-based loss detection, as is, for example, incorporated in QUIC. In other words, the end hosts detect loss, and then the L bit reports that loss into the network. Due to this design, in our setting, the server will report the overall loss on the downstream path. The second spin bit cousin is the so-called Q bit or square bit. As the name implies, it generates a constant square wave signal. Or in other words, it first transmits a certain number of packets with a set qubit and then a certain number of packets with an unset qubit. The network probe can then simply count how many packets have arrived in which phase and can thus derive the packet loss that has occurred here on the downstream 1 link. The third approach is then called the R bit or reflection square bit and builds upon the qubit. In essence, the end hosts deploy qubit observer logic and then report the number of observed qubits back into the network. Due to this design, the R bit in our setting covers the overall upstream path as well as downstream 1. Finally, we then have the so-called T bit, where we basically have one train of packets which is reflected several times between the server and the client. Mapped to our setting, our observer will now only be able to compute the packet loss that has occurred on the overall link. So from the time that the train has left the observer in the one direction until it has entered the observer again from the other direction. As we can already see here, the approaches differ in which parts of the network they actually cover. And this is already the first important decision factor when we want to decide on which of these approaches we want to choose. The second aspect would then be the measurement accuracy. So how accurate can we actually determine the packet loss rates? This directly leads us to our contribution, because what we have done is an experimental evaluation of the 4 spin-bit cousins using a mininet-based testbed. At this point, it is very important to have a fair comparison between the different approaches. And this is why we induce packet loss only here on the downstream 1 link, because that is the only link that all of the 4 approaches can actually cover. We've then investigated 3 different scenarios. In the first setting, we have induced random packet loss on the downstream 1 link. In the second setting, we have induced burst packet loss, and for that we have used the simple Gilbert model. And then finally, we've also considered the impact of different flow sizes on the measurement accuracy. In this talk, I will mainly focus on the first setting, so let's get directly into it. The main goal of our random loss scenario was to find out how well the different approaches perform under ideal circumstances. For this, we use symmetric traffic and disable congestion control so that there's a constant flow of packets. We then transmit roughly 1 million packets in each of our experiments and perform 30 iterations for each of our settings. We then report the cumulative loss rates that the different approaches have derived at the end of the experiments. In addition to the 4 approaches, we also track the ground truth, so how many packets have really been lost. What you can see in this plot is on the x-axis the configured loss rates, and on the y-axis the measured loss rates. If we now look at the results of all the 4 approaches, we can see that they are mostly very close to the ground truth, especially for higher loss rates. The only thing that stands out here is that the T-bit is not that accurate for low loss percentages, as evidenced by larger confidence intervals here. The main reason is that the T-bit includes 2 pause phases, and thus it doesn't actually cover the whole traffic. Next, we wanted to find out about the timely behavior of the different approaches, and thus looked at individual measurement runs. What you can see on this slide are the first 10 seconds of one hand-picked measurement run, where we had configured a loss rate of 1%. Looking at the L bit, we can see that it closely follows the ground truth, although there's always a slight timely delay. This is reasoned by the fact that the L bit depends on the end-host-based loss detection, which takes a bit of time until it actually deems a packet to be lost. Next, looking at the Q bit, we can see that it also follows the ground truth quite closely. We can also identify the longer algorithmic intervals, and the Q bit actually represents an interpolation of the ground truth. Next, looking at the R bit, we can see that it is significantly higher than the others here in the beginning. And also it starts later than the other 2 approaches. This is due to the fact that it builds upon the Q bit and first has to wait until the first iteration of the Q bit has succeeded. However, in the long run, it then also follows the ground truth quite closely. Finally, looking at the T-bit, the previously mentioned longer algorithmic intervals are now really visible because it is the only one to only produce 3 readings in the first second. Additionally, it also has the highest fluctuations in the measurements, and takes really long time until it gets close to the ground truth. So summarizing, it can be said that the L bit is the closest representation of the ground truth, while the Q and R bit are not far behind. Only the T bit struggles a bit and takes a long time to get close to the ground truth. Let us finally get back to the question stated in our title. So which spin bit cousin is here to stay? Well, solely based on the measurement accuracy, the L bit seems to be the best choice as it closely follows the ground truth. However, it depends on the end host loss detection, and there's always this slight temporal delay between the actual packet loss and its reporting. On the other hand, we've seen that there are longer algorithmic intervals for Q, R, and T, and these come with two disadvantages. First, there's a decrease in accuracy when they are subject to burst loss, as is evidenced in our second experimental setting. What we did is configure increasing average burst sizes, and as our results indicate, the Q, R, and T bits struggle if the burst sizes increase. The second disadvantage of those longer algorithmic intervals is that they prolong the time until the measurement stabilizes. These results now stem from our third setting, where we investigated different flow lengths. As is evidenced in the plot, the different algorithms start their measurements at different times. So the L bit starts first, then the Q bit joins, afterwards the T bit joins, and finally the R bit joins. This observation is especially important if we want to observe short flows or if we want to have fast measurements. However, in the long run, all the measurements start to stabilize at the same time, so at roughly 1 to 2 megabytes. So overall, the measurement accuracy seems to be suitable in all of the 4 cases, although there are, of course, differences in them. But which of those approaches now to choose? I think that another property of those approaches will eventually be the deciding factor when choosing which of them to deploy, and that is their path segmentation properties. These eventually decide on how closely the network operators will be able to localize loss, and thus it actually depends on the needs of the operators on how fine-grained they want to localize the loss in their networks. Because from a measurement accuracy perspective, all of the approaches should provide reasonable results for that. Thank you very much.
We have time for one question to Ike. Thank you for your presentation. Let's see, and then let's see if I see anyone in the queue right now. So while people are thinking, let me try one question to you, Ike. Do you think, have you thought about trying to measure the duration of packet loss burst? And do you think that would be feasible with the scenario that you have?
So basically you mean like how long the individual bursts that we have occur? Yeah, so basically that is not directly the intention of the different techniques that we have there.
Yes.
And I actually didn't come up with them myself. So I don't think that those techniques are that feasible for that. Yeah, there are ways of determining how long certain bursts take. But I think that is mainly only possible for the Q and R bits in that case, because the others are not that feasible for that.
Okay, thank you very much for. And Cedric had the question, and I guess it disappeared from my screen.
Yeah, he's actually
do you have a
stated
question?
the question in the chat, I think.
Oh,
if you like.
Can you speak?
Yeah, I can speak. I was just wondering if that instrumentation had an impact on the packet loss rate. So if you had all this bits to measure the packet loss, do you change the actual packet loss rate that you observe in the network?
So in our setting, we only had like this artificial loss. So in that case, we didn't really impact the actual packet loss rates. And I don't actually think that in reality that will be the case, because as it is right now, the spin bit.
We're ahead to it, basically.
Yeah. That's what I was about to say something about. So basically, the people in the IPVM working group are thinking about adding the lost bits to the 2 reserved bits that are still available in the quick short header. And in that case, that wouldn't really, so we would in that case only use currently unused space for that. But obviously, if we add additional bits to the overall transmissions, then that might have an impact. Although I don't, or I am not able to quantify that right now. But that's, I think a valid thought about those additional bits in that case. Yeah.
Okay, I guess we deferred further questions to the panel. So thank you very much. So
Thanks.
very nice work. And let's go to the next presentation. I guess the presenter, we're going to be Saidi from Max Planck Institute. He's a PhD student in computer science. Please, can start the presentation, please.
Hello everyone, welcome to my presentation. I'm Jawad Saidi, and today I am going to present our work on detecting consumer IoT devices through lens of an ISP. Consumer IoT devices have grown extremely popular recently, and it has been projected that the number of deployed IoT devices will surpass 17 billion by 2023. These devices provide a wide range of services, from smart speakers to smart appliances, TVs, and surveillance cameras. However, it has been shown that these devices can be exploited, and one notable example is the Mirai attack, where millions of exploited devices participated in launching one of the large-scale DDoS attacks that crippled parts of the internet and service providers. Moreover, these devices can be exploited to exfiltrate private user information without users' knowledge or consent. These problems brings us the question for us as network operators: can we identify and locate IoT devices that are connected to our networks? This problem can be studied in different networks, from small office to campus networks to even to large service providers. We collaborated with an ISP of 15 million customers, and we wanted to study this problem at the scale of an ISP. However, detecting IoT devices at the provider level is not an easy task. The reason is that traffic patterns across IoT devices are diverse. There have been some recent work that suggested that we can deploy some agent inside the premise of a customer. However, it's not scalable, and it is privacy intrusive as well, and active measurement approaches that won't work if the devices are located behind a net. Moreover, if we want to do deep packet inspection, we will face serious privacy concerns among the customers of an ISP. One of the readily available data sources are flow capture utilities such as NetFlow and IPFix. These data sources are already collected by service providers for their other operational purposes. These data sets are sampled, and they don't contain any payload, which means that they contain only headers of the packets, like source IP, destination IP, and so on. This brings us to the question of whether we can detect IoT devices using this limited, passive, and sparsely sample flow data in the wild. And if yes, at what granularities can we detect them? And how fast can we detect them? And how are IoT devices deployed today as observed in flow data? The key insight of our work is that devices that we've studied have shown repeating patterns of communication that appeared even in sparsely sampled data. We generated detection rules using extremely limited packet fields. And we were able to detect devices or generate rules for detection of devices from 77% of the studied IoT manufacturers. And we detected devices in a dataset from an ISP from within minutes to hours. We leverage the fact that IoT devices, in order to provide their services, they have to communicate with certain backend infrastructure. And if we focus on the destinations contacted by these devices, can we find out which of the subscribers of this ISP have which type of IoT device? Our methodology has 5 steps. First, we generated ground truth IoT traffic. Second, we check whether we can see traffic from a single device, from a single vantage point at ISP, the dataset from an ISP. And third, we identified which domains, IPs, and port numbers can be used to generate detection rules for different devices. And then, of course, we cross-checked our detection rules. And finally, we applied our methodology on a data set from a large European ISP. Next, we generate ground truth IoT traffic. How we do it? We set up 2 test beds containing 56 unique IoT products from 40 vendors in these 6 different categories. We trigger devices to generate IoT traffic. And next, we connect our test beds to a home vantage point inside the premise of ISP. And push back the IoT traffic to the internet and captured IoT traffic at these different locations as shown in the figure. We observe IoT activity from more than 64% of devices in our test bed in the ISP dataset. The next step is to basically identify which domains, IP addresses, and port numbers that we have generated in the ground truth traffic can be used to generate detection rules for finding IoT devices. As it's an involved process, I'm not going into the details, but as an overview, we have generated detection rules at 3 different levels of granularity. The finest one is the product level. Well, we can say what type of product it is, for example, if it's an Amazon Echo or not. And the next level of granularity is the manufacturer level, where we could only say it's a Samsung device. We could only say what's manufacturer. And the coarsest one is the platform level, where we could only say it's an IoT device, but we couldn't say what product or which manufacturer it is. The generated rules account for 77% of the manufacturers in our test beds. Next, we apply our methodology on a data set from a large European ISP. This ISP has more than 15 million customers. In this figure, we see the duration of the data set that we have observed, and in the y-axis, we see the number of unique subscribers that per hour that had the inferred IoT device. What we see here, we were able to detect more than 1 million subscribers with Alexa-enabled devices. Alexa-enabled device is any device that responds to Amazon Alexa voice service commands. We also observed some diurnal patterns for Alexa and Samsung IoT devices. The next question is that what happens if we increase our observation period? Here we see this same plot as previous plot, but with the 24-hour observation period. We see here that increasing observation period help detecting even more IoT devices. Next takeaway is that we see that the number of detected devices are stable, and there is not a lot of there are not a lot of fluctuations in the number of devices. In general, we detected IoT activity for 20% of the subscribers of the ISP. Now, if we zoom in on this 32 IoT device type, we will have this plot. Here, in the x-axis, in the left part, in the y-axis, we see each individual device. In the x-axis, again, number of devices, in the number of devices per day, 24 hours, and they are also categorized according to their ranking in the country, in the Amazon ranking in the country of ISP. For the ones that we didn't find a ranking, they are put into other category. What we see here is that device popularity in the Amazon and ISP look correlated. Our methodology has its own limitations. First, generating rules requires studying a range of manufacturers' products. And if the domains and IP addresses that devices are using change, then we have to also update the rules. And if the devices do not show or do not have enough activity, it will be challenging to observe them in the sample flow data sets. In conclusion, we have shown a methodology to detect IoT devices based on limited sample flow data. We detected devices from more than 77% of studied IoT manufacturers in a large ISP by considering minutes to hours of data, and both popular and not so popular. In future, we want to identify non-essential traffic generated by IoT devices at the scale of an ISP. If you are interested in the domains and signatures that we've generated to detect these devices, you can either scan this QR code or visit the following URL. Thank you for your attention.
Thank you very much, Saeed. We have time for questions. One question, please. Okay. Okay, so yes. Do I hear anyone? No one in the queue. Okay. I have a question. Do you use just ports and IP address, source and destination IP address and ports, or do you use anything more for the rules?
For the rules, we use port protocols and destination IP addresses.
Protocols as well. Okay.
Yes. Yes.
Okay.
And okay. We also we generated rules to generate finding which IP addresses to use. We use the domain names first, because we have captured the domain names in the lab. Because we cannot use all the domain, we cannot use all the IP addresses that that are contacted by the devices. Some of these IP addresses belong to generic infrastructure like Akamai or some cloud services, which are contacted by large range of users and devices.
Mm-hmm. Okay. And you identified in your presentation, you said how many different IoT devices you were able to identify?
Yeah, so we had 56 unique IoT devices from 40 manufacturers, and we were able, if I remember correctly, for 33 unique devices and 35 unique devices. We were able to do this, but some of these devices belong to same manufacturer, and for those devices we could only say what is the manufacturer of this device, and not only a unique product.
Okay, very nice, interesting, and you said that you can share that, right? With the community, right? So,
yeah.
Okay, I have one question from David Oren. Could you please speak, please? David? How do I...
What glitched on unmuting. So I assume that as an owner of one of these things, I really ought to use a VPN so that the ISP can't see my IoT devices?
Yes. If you use a VPN, then we only see VPN traffic.
So what do you think the privacy implications of your local ISP being able to fingerprint all these IoT devices in people's houses?
There are multiple use cases for that. The first one is that if a device is known that being infected or participating in a larger scale attack, ISPs can notify the users and the owners of that device and say, okay, you have a device that is infected. And it has been shown in case of Mirai attack where ISPs were actively engaging in notifying customers with the infected devices and even taking extreme measures, for example, by redirecting the traffic to a portal and saying, okay, you have this device that is infected, please do something about it.
Well, that'll work
Yes.
for about 5 minutes until the malware guy figures out how to hide the identity of the device.
Okay, you mean that once you know that this customer has this device, of course, with the consent, and it should be an opt-in service, not without a customer's consent. You can always you will know that this customer has, unless this has this type of device, and and you don't need to repeatedly detect the same device for the customer, unless if the device is moving from one customer. This device is only active for a few minutes in that customers. And in our setting, the subscribers were home users and or fixed subscribers, and not a mobile one.
Thank you.
So thank you very much. I guess we defer for the questions for the panel. We have to move on because of timing. So thank you very much, Said.
Thank you.
Very interesting. And so please, the next paper will be presented by Simon Bauer, who is at the Technical University of Munich. He's a research associate there. So please, the video.
Hi everyone, my name is Simon Bauer. I'm a research associate at the Technical University of Munich here at the Chair of Network Architectures and Services. And today I want to talk about our work on the evolution of Internet flow characteristics. As we all know, there's ongoing change on the Internet regarding new technologies, adapting user behavior, or changing Internet services. We are all aware of improving network expansions. We all observed the smartphone boom during the last decade. We are aware of the Internet of Things that rises, and of course, we know about audio and video streaming services. At the same time, previous studies present methodologies to survey flow characteristics like flow duration, flow size, or flow rates. But recent insights into flow characteristics in the Internet are rare. And therefore, our paper pursues the question how flow characteristics changed during the last few years. To answer such question, our paper surveys the distribution and correlation of flow characteristics and applies different taxonomies to assess the relevance of heavy hitter flows in the sense of elephant flows, but also in the sense of so-called big fast flows. Well, before we start talking about our methodology and our measurement results, let me briefly introduce a scalable flow analysis tool implemented in Go. That provides large scalability due to parallelized packet parsing and flow aggregation. The tool is published as free and open source with our paper. The tool consists of 5 major components, which are illustrated on the right. So the first component is a reader that reads packets from a PCAP file. That we have multiple parsers that extract packet features from such read packets. And those packet features are then written into a ring buffer component that is proposed to reorder packets. Well, a regular routine then writes such reordered packet information into pools where we collect package features per flow until a flow terminates, and after its termination, flow data is written to the metric component, where we then calculate our flow characteristics. Let's talk about flows. We identify flows based on the IP5 tuple, as we will focus on TCP traffic for our study. We identify the start of TCP flows with a three-way handshake, of course, and we terminate a TCP flow when we observe a connection teardown. If there's an idle period of a flow for a certain timeout period, or we observe a freshly established three-way handshake of a IP5 tuple that is already tracked. For identified flows, we calculate the flow size in the sense of the sum of layer 4 payload sizes. We calculate flow duration as the time interval between the first and the last packet we observe, and we calculate flow rate at the average data rate based on flow size and flow duration. For our study, we compose a data set consisting of 28 traces provided by KIDR. Such traces have anonymized IP addresses and no layer 4 payloads. And each trace provides 1 hour of traffic that is captured at a 10 gigabit per second ISP backbone link. As illustrated below, on the timeline, we select 23 traces taken in Chicago between 2008 and 2016, and 5 traces taken in New York between 2018 and 2020. As you see, we have 3 periods without traces for several months. So on average, we select traces in an interval of 3 months, but there are 3 intervals without traces, larger intervals without traces, because there are simply no traces available. Well, and regarding pre-processing of such traffic, we only consider TCP flows that are longer than or equal to 100 milliseconds. This is also done by related work and proposed to filter out quite short flows, because calculating flow rates or calculated flow rates may falsified for short flows in case of single packet flows, or if all packets are sent back to back. So let's talk about selected measurement results. So regarding the evolution of heavy hitters, related work proposes a definition of heavy hitter traffic based on the 99th percentile of a characteristic. So the 99th percentiles of flow duration, flow size, and flow rate. So we analyzed the evolution of such 99th percentiles over time, as you can see plotted here on the right. Let me point out 2 major findings. So regarding the 99th percentile of flow duration, here on top of the plot, we observe that there's only little increase during the years 2008 until 2013, but afterwards we observe an increase by factor 1.5 between June 2013 and March 2016. A further major finding of that analysis is the increase of the 99th percentile of flow rates, which refers to the bottom plot here. And here we observe a clear trend towards larger flow rates in the 99th percentile, i.e. an increase from around 400 kilobits per second up to 800 kilobits per second in 2015. Next, we were interested in the relevance of such heavy hitter traffic. Therefore, we calculated the share of transmitted bytes by such flows within the 99th percentile for each flow characteristic. We did not find a specific trend over time, so here the table shows the average across all traces taken in Chicago. In the second column, in the right column, we see the share of bytes transmitted by different percentiles, and well, especially the flows within the 99th percentile of flow size represent a large share of totally transmitted bytes, with nearly 90% of all TCP bytes transmitted by such 1% of flows. Further, we had a look at so-called big fast flows. So Zhang et al. Introduced a 2-2 taxonomy based on 2 threshold values to group flows regarding their size and their flow rate. And we had a closer look at the relevance of such big fast flows, which are represented by only a small share of flows, but as we will see, have a large relevance regarding the share of bytes that they transmit. So we define 3 threshold pairs. The first pair refers to the original threshold values from Zhang et al., i.e. 100 kilobytes regarding size and 10 kilobyte per second for flow rate. And then we increase the thresholds by 1 magnitude for pair 2 and pair 3. Let me highlight the increase of the share of bytes transmitted by the second threshold pair illustrated in green. So here we observe an increase of bytes transmitted by big fast flows between 20 and 30% for traces in 2018 and until 2010, up to between 40 and 50% of all bytes transmitted by TCP. For more recent traces taken in Chicago, the values for the New York data set are smaller, which can be traced back to a larger share of small flows for such traces. To conclude my talk, let me summarize our findings. So as we have seen here in the talk, we observe a significant increase of the 99th percentiles of flow duration and rate. We find a large significance of heavy hitters regarding the share of transmitted bytes. And we observe an increase regarding the relevance of big fast flows during the past years. Further, and not included in the talk, but in our paper, you will find an analysis of the distribution of flow characteristics over time and a study of correlation coefficients between the flow characteristics, where we can confirm findings of previous studies, especially regarding a strong positive correlation between flow rate and flow size. And that's it from my side. And now I'm happy and looking forward to answer your question.
Very much, Simon. Thank you very much. And have time for one question before the panel. Okay, I guess people are differing for the. I have one quick question, perhaps. There has been a change in flows since the pandemic. So are you looking into that, the change of the flows in the last year?
Yes, so we did not do that yet, but we definitely plan to do that. So as you have seen, we now worked on the KIDA data set. Well, and KIDA provides 1 trace per year, and so we're looking for further data sets that allow a more fine-grained study, and especially regarding the pandemic during the last few months. So this will be a topic for the future.
Sure, very nice. There is one question here from Jen. Can you please speak?
Hi, Simon. Thanks for a nice talk. I was wondering, I'm not sure about the data set. Do you know something about how the parallelization of flows changed over the years? So like the change from HTTP1 to, let's say, QUIC or HTTP2, where now things start to get parallelized over the same connection, so you would see less parallelization. Do you see something in those traces, or is that hidden through the anonymization?
So we did not have a closer look on that aspect of the data set. So I can't really answer that question. But what I can tell you is that the IP addresses in the data set are anonymized. So I'm not sure whether this affects the study you just proposed.
Okay, so thank you very much. I think it's better to invite all the speakers to the room and now and collect questions for everyone. So I'm not sure how to do that, but I think yes, okay, it's coming. Okay, I think we have everyone here. So do I see any more questions from the audience? Or you can ask questions for each other also. That's in fact very nice audience. We had 80 people through the audience. So okay, there is Ali. Can you speak, please? I guess there is one in queue, Ali Hussein. You can just speak, please.
There was a permission, so I just allow it. Can anybody hear me?
Yeah, now yes.
Yeah, so yeah, the question is for the Simon. Do you see any anything related to the? I just walking over your paper. So, what is there any correlation between the the IPv6 and the port correspondingly being used, because the microservice architecture is dominating the development? So I'm just have you considered that aspect as well?
Stop typing or turn off your microphone.
So I'm not sure whether I understood you correctly because the audio was not so good.
Sorry, I can repeat.
So if the question, if I understood it correctly, the question is whether there are some differences regarding IPv4 and IPv6 traffic, right?
Yes.
Okay, so we did not do an analysis of this in depth. So the current state of the analyzer hashes IP addresses to provide faster handling and further step of anonymization. So we're currently working to add IP addresses in plain, and then we would able to have a look at IPv4 versus IPv6 too.
Okay, thank you.
So anyone else? Let me remove Ali from queue. Anyone else for questions? And I guess if not, I have a question for Justin for the first talk. Do you foresee in your presentation and your environment any performance issues to implement the solution, the collection of all the results, so the performance overheads? Have you thought about that, or if any, or do you foresee any problem?
Yeah, so that's a good question. So can you hear me? Yeah?
Yeah, perfect.
Yeah, okay. So actually the overhead is, again, it's all on IOM. So the overhead introduced by the cross-layer telemetry is just a netlink call. So that's not that big. And all the overhead is on the IOM side. And so we have already measured the impact of IOM in another paper. And so unsurprisingly, the more you insert, the more it drops. So you have to find a compromise depending on your hardware and a lot of things.
Okay. So perhaps you see that more when in the real implementation you tune it better than you make.
Yeah, and by the way, just a small notification to operators that IOM is now available in the kernel. So it's from 2 or 3 days, and it will be available in 5.14 version. So.
Okay, great. Thanks. Very nice.
Thank you.
People, yes, Colin, please.
I have a sort of fairly general question for perhaps most of the presenters. The talk about spin bits. I mean, the spin bits obviously came from Quick initially. For the other talks, does the presence of Quick and the deployment of Quick affect the types of systems you're building or the behaviors you expect to see?
So is the question for everyone, Colin, or just?
I guess for everyone apart from the spin-bit talk. Although I'm happy for everyone to answer it.
Okay, who wants to start that?
So I can start if you want. The answer is no, there is no problem. So short answer, quick.
Okay, that's easy. Great.
Anyone else would like to get
Yeah,
on that?
so we also considered to detect quick traffic in our data set, but there was not a significant share. So we did not have a closer look.
Okay, but the tools can detect it.
Yes, and also the analysis tool we implemented is capable to be extended for further headers and protocols. So also this would be feasible.
Okay, good.
Anyone else would like to? Yeah, I can comment on this.
Yes,
as far as I know, since in our work we are mostly focused, we don't look into the header at all, and we probably won't be able to distinguish between Quick and other protocols. I would say it won't affect detection because we are mostly focusing on the destinations, or something like that.
Yeah, but it doesn't help obfuscate the traffic. Yeah. Okay. Thank you.
Thank you. Anyone else for questions? I have one quick question for Ike. Did I pronounce your name correct? Yes? Okay. Did you contrast the measurements you talk about in your paper, like a passive measurement, which it's good, but did you contrast for packet loss of active measurements, the difference of doing that, or do you see any reason to compare?
Yeah, so in our work, we didn't do that. So we were just interested in finding out how well the different approaches can actually detect the loss that's happening, and actually the normal traffic that we were sending was kind of the active measurement part on that. And I think the general idea of those approaches is also to kind of not have to use active measurements, so that we can keep the additional overhead on the network low and just measure it on the already passing traffic without having to actually insert additional traffic. So we didn't do.
No, I understand. My question was more like if you would think would be try good to compare one against the other, not in terms of overhead. Of course, the overhead it's much more in active measurement, but in terms of accuracy, you don't see any difference of doing that. Or do you expect any difference?
Yeah, so I think the main thing is that if you use active measurements, then you won't be able to get the loss that is happening in your network under normal conditions, and thus you would always kind of have a different picture than what you would get when you just use those different loss techniques here, and so I don't think that this contrasting at that point is something that I would consider.
Okay, thank you very much. Any other question? Folks in the audience, we still have time. Do I see anyone trying to ask questions? Hello? Please raise your hand and you show up in the queue. Well, let's see. Okay. I have a question to Simon. I guess in your paper you say that 70% of flows transmit at a rate between 1 kilobit per second and 100 kilobit per second. I kind of wonder, is that do you expect this transmission rates, or did I get it wrong? It seems that's slow transmission rate. There is any reason for that, or do you expect that, or I'm just interpret it wrong?
So if I understood you correctly, the question is, or you mentioned that we observed a large share of flows within quite a small range of the rate spectrum, right?
Yes.
Yeah, so spontaneously, I don't have an explanation for this. So we plan to have a closer look onto ports and even IP prefixes that may allow us to differ between different kinds of flows. Then I might be able to answer your question.
That really interesting. Okay. Thanks a lot. Folks, well, I guess people are, maybe in Europe, it is late in Europe, not for me, but so people want to sleep. So very nice talks. I learned a lot from you. So I hope the audience enjoy it. I say we have a large crowd watching. I certainly will refer your work to my students. So thank you everyone for being here. It was really nice, and hope the audience enjoy. So thank you very much for everyone. Andra, you want to say something? Oops, I guess we can close the session for today. Okay, so thank everyone.
Thanks.
Bye.